Hello and welcome. This topic is about pressure. Before we look at the definition of pressure and other things which are related to pressure, let's ask ourselves, why should we want to study pressure? Think about the daily implements that you use. For example, think about a knife that you use for cutting things. Right now I'm thinking about this utility knife. When I look at the blade is very, very sharp. That is how I describe that. But we are going to see that we make the blade to be as sharp as possible. That means we are reducing some kind of area of contact between the blade and the object which I'm cutting. Let's say I want to cut this material here, and I have to apply a certain amount of force. You find that when the blade is blunt, you will have to use a lot of force to cut this material. It's like cutting the same material using this other side of the blade. You can see I have to use a lot of force in order to cut because this side is blunt. But the moment I use this side, see, it cuts the material very easily. So studying pressure makes us to understand why we want to use sharp objects such as knives, nails, when we want these objects to penetrate other materials. On the other hand, think about a car. Why is it that some cars have got very many tires, while some have got very few? Think about a van, a small van. It only has probably just 4 tires. But when you think about a truck, it may have 22, 26, or even more than those number of tires. Why should it have so many tires? And why is it when it is coming from the coast, when it is heavily loaded, all the tires are in contact with the road? But when it comes from the mainland back to the coast after offloading, you find that it has retracted some of the tires. Some of the tires are retracted upwards. How do we interpret these things that we see on a daily basis in terms of scientific terms, such as pressure? So studying this topic will enable us to understand these concepts or these situations in our everyday life. Once we understand them, then we are able to design new situations which make use of the same concept. So basically put, that is the reason why we would want to study pressure. Now let's go into the definition of pressure. Hello and welcome to this chapter. In this chapter, we want to talk about pressure. There are several things we'll talk about pressure, and I want to go straight to the first item. When we encounter a physical quantity for the first time in physics, the first thing we want to do is define it, state its SI unit, and see whether we can be able to define the unit of that physical quantity if it has the name of a person. So let's go straight to the definition of pressure and the SI unit of pressure. You usually get this kind of question: define pressure and state its SI unit. Sometimes they go ahead and ask you to define the SI unit of pressure, which is the Pascal. You get a question like, define the Pascal. So in this first section of this topic, we want to deal with these two things: definition of pressure and the definition of its SI unit, which is the Pascal. So how do we define pressure? We have already encountered another physical quantity, although we have not defined it in the actual sense of definition. We are still going to use it, and this is force. In the previous chapter, we looked at force and we said that At this level, you could just say that force is either a push or a pull, and it's got the SI unit Newton. But when it comes to the definition of force, we will encounter that when we deal with Newton's laws of motion somewhere in our third year of study. The other physical quantity that we have already encountered is area. Area is a measure of surface and its SI unit is square meters. So we have encountered these two physical quantities. Now we are going to combine these two physical quantities, force and area, and come up with another physical quantity which we refer to as pressure. Remember what we said about derived physical quantities. A derived physical quantity comes about when we combine two or more physical quantities that we have already encountered. And by the way, for you to be able to define a physical quantity in terms of other physical quantities, that is, in order to come up with a new physical quantity, you must have encountered those other physical quantities which you want to combine. That is why I'm referring to force and area, because we have already encountered these two. So, how do we combine force and area to get pressure? You can imagine the force exerted by an object, such as maybe a box or maybe my calculator on my hand. There is an amount of force. First of all, there is contact between this calculator and my hand. There is that area of contact. And then the amount of force that this calculator exerts on my hand is exerted within that area. The other thing is this: what is the name of the force the calculator is exerting on my hand? The name of that force is weight. We have already encountered weight as the amount of gravitational pull on the calculator by the earth. So the earth is pulling this calculator downwards. So as far as my hand is concerned, my hand interprets it like the calculator is exerting a force on my hand. But actually, if we trace that force, we find that it is not produced by the calculator on my hand. It is produced by the attraction of the calculator by the earth, and therefore my hand comes in to prevent that calculator from moving down. I hope I'm not confusing you here any further. I just want to clarify the force which the calculator exerts on my hand, and it exerts that force within a certain area. If my calculator was to lie on its smallest area like this, it still exerts the same amount of force, but the area of contact now has reduced. If you find the ratio of the force the calculator exerts on my hand to the area of contact between the calculator and my hand, you get a new physical quantity we call pressure. So pressure is the force exerted normally on a unit area. The force exerted normally on a unit area. I also want to explain that term, normal, what it means. So let's look at the actual definition of pressure: force exerted normally on a unit area. So first of all, we see that over here we are dividing the force and the area. We are dividing the force and the area to get pressure. What does it mean by normal? This is what it means. Again, when I go to my hand and the calculator, the area of contact is in the horizontal plane. The force exerted by the calculator on that area is vertically downwards. So the force is in the vertical plane while the area is in the horizontal plane. The angle between the vertical and the horizontal is 90 degrees. And that is where the name normal comes from, or the term normal comes from. We say that this line is normal to this other line when we mean that the two lines are perpendicular to each other. So in this case, the force and the area, they are perpendicular to each other. We have already said that force is a vector quantity, it's got direction. So this force is acting vertically downwards, but the area is horizontal. The angle between the two is 90 degrees. So let me do some inking of this slide here. So we have agreed that the area, I'm going to try and draw a nice horizontal plane. That one is a horizontal plane, and the force is perpendicularly downwards. You agree with me that at this particular point whereby the line of action of the force makes contact with the area, you find that it is 90 degrees. So the area and the force are perpendicular to each other. So in the definition of pressure, it's not enough to just talk about force per unit area or force exerted on unit area. You must bring out this term here, normal. You must state clearly that the force and the area are normal to each other. The equation which stems directly from this definition is force over area. Therefore, pressure is equals to force over area. It is an equation which reminds us how pressure is defined. Force per unit area. Force exerted normally on unit area. Now, force has got the SI units, newtons, while area has got the SI units, meters squared. So we see that newtons per meters squared will be the SI unit of pressure. Newtons per meters squared. So in a situation where you're asked define pressure and state its SI unit, it's simply pressure is defined as force exerted normally on unit area. And then the SI unit of pressure is newtons per meter squared. That is when you were answering that particular question. But in the notes, this is what you will write. Definition of pressure. You will write this, definition of pressure, and then immediately below that, you'll say pressure is defined as force exerted normally on unit area. Then just below that sentence, you will write this equation. Pressure is equals to force over area. Now, after that, you're going to say the SI unit of pressure is newtons per square meters or Pascal. But first of all, let's see what else is in this slide. Of course, it's exactly what I've said. The SI unit of pressure is Newton per square meters. Newtons per square meters, written like this. Newtons, this slash means that the Newton is being divided by the meters squared. It's called the slash notation. This or sometimes this one is written like this. You'll find that newtons, and then there is some space here. There is meters, and then raised to -2. This one here is sometimes written like this. This is called the scientific notation, and this is the slash notation. Now the Newton per meter squared is given the name Pascal. Pascal is the name of a person, and we have already said that when SI units are names of people, we write the complete unit, or we'll write the SI unit. If it is a complete word, then that word starts with the lowercase letter. In this case, it's lowercase p. But when we abbreviate the same SI unit, the letter now becomes uppercase. Look at the difference. This one is lowercase p, this is uppercase P. Just like we did with the Newton. I'm emphasizing this because I observed that several students did not get what I was talking about when I was talking about Newton, abbreviated with uppercase N, and the word Newton written in such a way that the word starts with lowercase n. So the same applies here, and I'm going to repeat it throughout our discussion in any topic where we encounter new SI units, and these SI units are names of people. So, understand, the SI unit of pressure is Newton per square meters or Pascal. Now let's see how that Newton per square meter has come about. By the way, I'd like to emphasize this, that sometimes in an exam when you want to write an equation, it's always good to write the equation, especially if it is a simple equation, using words. And then after that, you can use symbols, because after that, it is understood that P represents pressure, F represents force, A represents area. Then you can continue using the symbols in your calculation. When we are talking about SI units or units of a given physical quantity, we put that physical quantity in square brackets. So this is what it means. P in square brackets is read as the SI units of pressure is equal to the SI unit of force divided by the SI unit of area. And since the SI unit of force is Newton, the square brackets disappear, because right now we are not talking about the SI unit of this physical quantity. It is the SI unit itself. So the square brackets disappear here because these are the SI units of, to start with, force, the SI unit of area, and when we combine the two, we get the SI unit of pressure. So understand that. Let's look at what else we have there. But at this point, I think we are ready to look at the first problem, which involves calculations of pressure in solids. Let me see. Or there was one simple thing that was remaining. The definition of the Pascal. Definition of the Pascal. Remember, we have defined the physical quantity pressure and stated that pressure has the SI unit Pascal, and because Pascal is not among the 7 base units, it must be defined. So we want to define the Pascal. What is the Pascal? The Pascal is the pressure exerted when a force of 1 Newton acts normally on an area of 1 square meter. And that's exactly what we have here. So when it comes to defining the Pascal, as an equation, we say 1 Pascal is equal to 1 Newton of 1 square meters. In an exam, if you're asked to define a physical quantity, ensure that you define that physical quantity in terms of other physical quantities, or you describe how that physical quantity is obtained from the other physical quantities. That is what we mean by definition of a physical quantity. When you are asked to define an SI unit, be sure to define the SI unit in terms of other SI units, or units in terms of other units. For example, 1 Pascal is equal to 1 Newton of 1 meter squared. This is the equation which is associated with the definition of the Pascal. But in the same exam, once you're asked to define the Pascal, this is the definition that you should adapt. 1 Pascal is the pressure exerted when a force of 1 Newton acts normally on an area of 1 square meter. And let's pause at this point, and when we come back, we are going to look at calculations involving this equation. That is, we are talking about calculation of pressure in solids. So see you in a moment. Now that we have defined the term pressure, stated it as a unit, it's time to look at how we apply that equation in actual problem solving. Now, before I go to this, you find that in the definition of pressure, you could also use the term perpendicular. You could say pressure is defined as the force acting perpendicularly on a unit area. So the word perpendicular and normal, they mean the same thing. So let's go into this first example here. This question is also found in your course book. But I'd like us to try it out first. When you see that examples have been given in your course book, usually don't go straight into looking how they have been worked out. These are a trick that I usually teach my students. You take another piece of paper, you cover the area where the solution has been given so that you can only see the question. Then you try it out. Once you've reached a point where you think you have obtained the answer, or you reach a point where you think you are stuck, now it's time to look at how it was solved. Why is that skill important? Why is it preferable to just looking at the solution? It is preferable because when you are looking at the solution to a question, you will be looking for something. For example, you can use that skill with this video. You can pause the video, then get the solution to this question, and then play it back and see how we obtained the answer. So let's go straight to the answer to this particular question, where we are told a man of mass 84 kilograms stands upright on a floor. If the area of contact between his shoes and the floor is 420 centimeters squared, determine the average pressure he exerts on the floor. This one is similar to the example that I was giving. The example I used is that one of a calculator which is resting on my hand like that. The amount of force that the calculator exerts on my hand is its own weight, which acts vertically downwards. The area that I would use will be the area of contact between the calculator and my hand. At this point, I want to mention something else that I've seen students making a mistake in. And this is referring to the area of contact as the surface area. They say pressure is defined as force exerted normally on unit surface area. Don't talk about surface area. Surface area of this particular object will be this area plus this area plus this area plus this area. It is the total surface area of the object. But remember, the area that we are interested in is the area that is the area of contact between the calculator and my hand. That is the area that matters. So it is the area of contact, not surface area. So don't make that mistake. So the amount of force that this man exerts vertically downwards on the floor is equal to his own weight. And then the area of contact will be the area of his shoes, because he makes contact between himself and the floor via his shoes. So the area of contact is equal to the area of his shoes. So understand that. The next thing is to understand that force is in newtons, and so is the weight of this person. Remember, there is a difference between mass and weight. So we have got to convert the mass of that man into weight in newtons. And at this point, I'd like you to recall the relationship between the two. I'd like you to recall this. Just recall that the force exerted is equal to the weight of that man, and the weight of that man is related to the mass via this equation. So, this is the value of the gravitational field strength. That's why it is given here. Take G to be 10 Newton per kilogram. What does this mean? The gravitational field strength means the amount of force that the gravitational field exerts on unit mass at that particular point. So it exerts 80 newtons on every 1 kg mass. So how about if the mass of this object is 84 kilograms? So you multiply by 10 Newton per kilogram. You'll see that this cancels out with this, and this gives us 840 newtons. So in using the equation, pressure is equals to force over area. We have already worked out the force. How about the area? There is only one thing that will prevent us from using this value directly. It is the units. The SI unit of area is meters squared. I'd like you to remember that 10,000 centimeters squared is equal to 1 square meters. So this conversion unit will help you to convert 420 centimeters squared into meters squared by dividing 420 by 10,000. 10,000. And you're going to get this area to be in meters squared. So this one will give us 0.042 meters squared. Now we are in a position. So the area, this is the area. Remember, now we want to use this equation. We've already got the force, which is 840 newtons. We have the area, which is this much meters squared. We can now straight away go to the calculation of pressure, which is force over area. The force is 840 newtons. Now arm yourself with a calculator, because I'd like you to work out these values together with me. Usually when I'm teaching, I also expect that there at home you have got a piece of paper, you've got your notebook, you have got a calculator, and you're working out these values with me. So let's work this one out together. 840 divided by 0.042 will give me 20,000 newtons per meter squared, or 20 pascals. So this one is 20,000 newtons per meters squared. Something else that I want to mention here, I'm going to write it in a different color so that you can see that it's wrong to do that. What is it that I want to write down? I want to write down this. Sometimes I usually get these students, they write down something like this: newtons slash meters, then something like this. Why is it wrong to write this? You have combined the slash notation and the scientific notation. That is unacceptable. Use one of them. Either use the scientific notation or use the slash notation. One at a time. Don't mix them. Another thing that you will find in your textbook is they're saying that pressure can be measured in newtons per meter squared, pascals. It can also be measured in millimeters of mercury, centimeters of mercury, or even atmospheres. We will use those other three units, millimeters or centimeters of mercury, or even atmospheres, when we are talking about pressure in gases and also pressure in liquids, that is pressure in fluids. But in solids, most of the cases we are using the SI unit, newtons per meter squared, or pascals. And that is how we would work out example 1. Let's look at example 2. Now here we've got example 2. In example 2, we are given a metallic block of mass 40 kilograms exerts a pressure of 20 newtons per meters squared on a flat surface. Determine the area of contact between the block and the surface. You see, this time they've given you the mass of the block from which the weight of the block can be worked out, and therefore the force exerted by the block on the ground. And they've given you the pressure. Now they want you to work out the area. The question is quite direct. Over here, when you come to the same equation, pressure is equals to force over area. It is the area that we are interested, so we have to make the area to be the subject of this equation. And I will take this example to show you how this is done. So this is what we are going to do. There are two methods that we can use. First of all, I can take this equation and put it in a triangle, which is like this. This usually applies when the equation has got only two factors. When I divide the force by the area, I get pressure. So you can see pressure is equals to force over area. When I want pressure, I cover pressure with my hand, and what is left is force over area. If I want area, I cover area with my hand, and what is left is force over pressure. And when I want force, I cover force with my hand, and then what is left is pressure times area. And let's use that first method, where we cover area with our hand, and we can see what is left is force over pressure. And we make this substitution direct. Remember, the force exerted will be the weight of this man, which is 400 newtons. I know you know how I've got that. I've multiplied the mass by the value of the gravitational field strength, as we did in the previous example. The pressure here is 20 newtons per meters squared. And definitely you will see that the area of contact is 2 meters squared. So this is the area of contact between this block and the floor. Let me show you the other method of getting this area. When you are given this equation, which is pressure is equals to force over area, and you want to make area to be the subject, what you do is you multiply both sides by area, in which case this area disappears. And then from here, you're going to make area to be the subject by dividing both sides by pressure. And again, pressure disappears from this side. And you can see now what is left is area is equals to force over pressure. So those two methods can be used. I'd like you to understand both of them, because initially this is the simplest one, and I have had students preferring to use this most of the time. But when the equations change, you may have to adapt this other method. And that is how you would work out example number 2. Let's look at example number 3. Okay, in example 3, we are told that a brick 20 centimeters long, 10 centimeters wide, and 5 centimeters thick has a mass of 500 grams. Determine the greatest pressure that can be exerted by the brick on a flat surface. and then determine the least pressure that can be exerted by the brick on a flat surface. So I'm going to use this question to discuss two factors which affect pressure in solids. But first of all, let's look at the situation that we have. This is the situation that we have. We have this brick here. It has a mass of 500 grams. So the amount of force it exerts on that horizontal surface is equal to its own weight. So first of all, you convert that mass into kilograms rather, and then convert those kilograms into newtons using the equation that we have used in the past two examples. Now this time, instead of them giving us the area of contact directly, they've given us the dimensions of this regular solid, which is a cuboid. It is from these dimensions that we can be able to calculate the area. So, for example, when it is resting on that small area, how much force is the block exerting on that small area, as opposed to when it is resting on the large area? You find that the force is the same because the force is equal to the weight of the block, which does not change. Don't confuse this with that situation where we say that weight of a substance changes from place to place. The place has not changed, so the weight of that object remains the same because the value of the gravitational field strength has not changed. So the force that the block exerts on that surface remains equal to its own weight, and that weight remains the same whether it lies on the smaller surface or on a larger surface. But the pressure calculated when it lies on a smaller surface, we will discover that it is greater than the pressure exerted when it lies on a larger surface. Why is that? It's because pressure is inversely proportional to the area. The smaller the area of contact, the greater will be the pressure. And that is the reason why we sharpen cutting objects. When we sharpen cutting objects such as knives, we are trying to reduce the area of contact between the knife and what is being cut, as it happens in the example that I gave at the beginning of this video, where I was using the utility knife to cut a piece of plastic. You find that a sharp knife means that the area of contact between the knife and whatever is being cut is very small. That means a small amount of pressure, a small amount of force can produce a large amount of pressure. And because the pressure is the penetration effect of this object into the softer material, we want it to penetrate that material as easily as possible using a small amount of force. And we can only make sure that this one happens by reducing the area of contact. That is why knives, it's easier to cut with a sharp knife than a blunt knife. We usually get this question in the exam. How do you answer that? It's because the area of contact between the knife and the object being cut is very small for a sharp knife, and therefore any force exerted or a small force will produce a large pressure which will be necessary, which may be the more than the pressure required to penetrate the material or to cut the material, so to speak. So I hope you get the point here. So of course the greatest pressure is exerted when the brick lies on the smallest area. How do we get the smallest area when we look at those numbers? When you look at those numbers, the only area that will be smallest will be between 10 centimeter length and 5 centimeter length. So this length here is 10 centimeters, and this one will be 5 centimeters. The height here is 20 centimeters. So in order to get this area, we'll just do 50. We'll just do 5 centimeters times 10 centimeters, where we get this area to be equal to 50 centimeters squared. When we divide 50 by 10,000, we get 0.005 meters squared. And it is this that we want to use in order to calculate pressure, which should be equal to the force. The force is the weight of this, which I hope you've been able to show that it is 5 newtons, divided by 0.005 meters squared. Another way of converting mass into newtons is to use another very simple conversion factor. On Earth, 100 grams will be equal to 1 newton. We can be able to show this. When you convert the grams into kilograms and then use the equation W is equals to mg, you will arrive at a very simple conversion unit. So let's go ahead and divide 5. I hope you're working along with me, and this gives me 1000 newtons per meters squared. So that will be the greatest pressure that can be exerted by the brick on a flat surface. How about the least pressure that can be exerted by the brick on a flat surface? We realize that will only happen if this brick now lies on its largest area. So we have already seen this. I will come back to this slide later on. Let's first of all work out this, where now the brick lies on its largest area, and that means that this length here is 10 centimeters, while this one will be 20 centimeters. The area is 10 times 20, which gives me 200 centimeters squared. When I divide this one by 10,000 rather, I get 0.02 meters squared, and therefore the pressure will be equal to the force, which is 5 newtons divided by 0.02 meters squared. That will give me 5 divided by 0.02, and I have 250 pascals on newtons per meters squared. You can see that when the area is doubled, the pressure will be halved. That shows that one of the factors which affect pressure in solids is area. So in a question where you are asked, state and explain factors affecting pressure in solids, area is one of those factors. When you say that pressure is inversely proportional to the area, you are explaining. So look for those two words, state. They are asking you to mention the factor. When you say how that factor affects that physical quantity, you are explaining. So pressure is inversely proportional to the area, and this is how we write it. This is 1 divided by area. If we want to put this information on a graph, if we did this as an experiment, we calculated pressure several times, we'll find that the graph is going to be exponential. It will be like that. I said I would use this question to explain the two factors which affect pressure in solids. The other one is the force exerted. Over here, this is 500 grams, which is 5 newtons. So the force is 5 newtons. This is 250 grams, which means it is 2.5 newtons. You can see that the force has been halved. When I calculate pressure here, which is force, which is 2.5 divided by the area of contact, the area of contact is still 0. I think it was 0.005 because it was 50 centimeters squared divided by 10,000, 0.005. The pressure exerted by this block, in this case, will be 2.5 divided by 0.005. And we find that it is 500 newtons per meters squared. How about the pressure exerted in this case here? It will be 5 divided by 0.005 meters squared, and this, like we saw, was 1000 newtons per meters squared. How has the pressure doubled? Or how has the pressure been halved? The pressure has doubled in this case because the force has doubled. Notice that the force has changed from 2.5 newtons to 5 newtons. So in that case, we say that pressure is directly proportional to the force. That means that when we double the force, this is the force. When we double the force, the pressure doubles, and that is what we get. So, understand this. There are two factors which affect pressure in solids. One of them is the area, the other one is the force. How does each one of these affect pressure? When force is doubled, pressure is doubled. That is direct proportionality. And it is written like this. And graphically, this is how we would express that situation. When we are changing the force, we are keeping the area to be the same. There's something else that I should be able to mention here. That in science, when we are investigating how a given physical quantity affects another physical quantity, we usually keep any other physical quantity that affects what we are investigating constant. In other words, for example here, we can be able to see that there are two factors which affect pressure. One of them is force, the other one is area. When we are investigating how force affects pressure, we are supposed to keep the area to be the same. And notice that here I changed the force. I had to halve the force when I come this way. I made the force to be halved, but I maintained the same area. How about in the previous situation? Let's go back there and see what we had. In this situation, notice that we are investigating how the area affects the pressure. We had to keep the mass of the object to be the same. Compare this mass of this object, the weight of the object rather, which is equal to the force that the object exerts on that surface. We had to keep that weight to be the same. That is why we use the same brick, but we turn it in different positions. And that is exactly what the question is asking us to do here. Calculate the greatest pressure that can be exerted by the brick on a flat surface, and then the least pressure. It's up to us to know that the greatest pressure is exerted when the brick lies on its smallest area, and the least pressure is exerted when the brick lies on its largest area. So, what is the variable that is kept under control, that is kept constant? By the way, when we keep a certain factor constant, we say that we have kept it under control. That is a proper scientific term, which is a variable which is kept under control. The variable kept under control in this situation is the force exerted. That's why we use the same brick in this side and when lying on this other side. And that is all we can say about example 3. Now, I also want to take this question to discuss or to outline the scientific procedure, especially when we are talking about dependent and independent variables. Let's go to the definition of pressure. We see that according to that definition, pressure is obtained from two physical quantities, force and area. The physical quantities from which pressure is obtained automatically become the factors which affect how much pressure is affected or is exerted in solids. That is one of the points that you can use to determine which are the factors which affect a given physical quantity. Which one comes first? We studied force and area first, and then we combined them to get pressure. It was not the other way around. There is no way we can talk about pressure if we didn't know anything about force and area. So it's force and area which came first. So that gives us a clue as to the factors which affect pressure. So those factors which affect pressure, we say that pressure depends on them. Scientifically, when it comes to expressing these factors on a graph, the dependent variable is plotted on the y-axis, while the independent is plotted on the x-axis. In this case, this one was area. I forgot to indicate this situation here. This is area. That is how area affects pressure. So the physical quantity which is affected by a change in the other one is referred to as the dependent variable. In this case, pressure is affected by the way area changes. So we deliberately changed the area from being a big area to a small area or vice versa. And then we saw how pressure was affected. That's why we are calculating pressure when the block lies on its largest surface and when it lies on its smallest surface. And normally we would say pressure is inversely proportional to the area. That is the correct way of putting it, because pressure is the dependent variable. It depends on area. It will be illogical to state this statement the other way around. It will be illogical to say that area is inversely proportional to the pressure. I've seen students expressing this, and I know the source where it comes from. It is the way you have learned that. But because you are listening to me as a student directly, then get it from me. In science, when we investigate how a certain physical quantity is affected by another one, we are very careful not to interchange them. For example, here we'll say pressure is inversely proportional to the area, and it remains like that. We cannot interchange and say area is inversely proportional to the pressure, because that will not make sense. We change the area, and then we see how the area affects the pressure. And then we see how the pressure is affected by what we have deliberately changed. That physical quantity which is at our direct control, which is the area, we can decide to change it. We can decide to double it. We can decide to make it half. We can decide to make it very small. That physical quantity which is at our control is what we refer to as the independent variable. Then when we change it and then we see how it affects the other one which is affected by the change that we've brought is referred to as the dependent variable. In science, we always want to keep every other factor which affects that physical quantity which we are investigating Every other factor is kept unchanged. It's kept under control. And you have seen how that happens. When we allow more than one factor to change, it will be very difficult to tell which factor is responsible for the change that we have seen. So, understand this. The dependent variable is always plotted on the y-axis, while the independent on the x-axis. It does not matter what the gradient represents. If the inverse of the gradient is the most important factor here, then we would bring it out. But when that one is not a factor, then let's follow the scientific way of doing it. Dependent variables on the y-axis, independent one on the x-axis. So that is what I wanted to add as far as dependent and independent variables is concerned, because it is something that is going to come out in most chapters in physics as we progress through our O-level physics. Now that we have looked at the definition of pressure, looked at the SI unit of pressure, and even engaged in calculations involving pressure, I'd like us to look at the first exercise in this chapter, which is exercise 4.1. But before we do that, let's look at some of the applications that I mentioned at the beginning of the video. And you are likely to encounter questions like this. Explain the following observations, of course, using the concept of pressure. Number 1, a person makes deeper marks while walking on soft ground in very narrow and sharp-heeled shoes than when in ordinary shoes with flat heels. Number 2, it is easier to push a sharp pin through a cardboard than it is to push a blunt one through the same material using the same force. Number 3, some vehicles such as transit good vehicles have many wheels compared to smaller vehicles. We usually get these questions for 1 or 2 marks in any one paper, and it is important that you display or you mention the idea of pressure. And then you also mention factors which are affecting pressure, because this one is about pressure in solids and the factors which affect pressure in solids. For example, when we look at the first one, a person makes deeper marks while walking on soft ground in very narrow and sharp-heeled shoes, such as this one here. You find that this one is likely to make dents, or if both of these people were to walk on soft ground, such as maybe a field of grass, you'll find that this person, the person who has high-heeled shoes, is likely to sink. This part is likely to sink into the soft ground compared to this person here. Why is that? It's because of the area of contact between the two objects, between the shoe and the ground. Notice that here the area of contact is very large when you're wearing flat-soled shoes than when you're putting on high-heeled shoes. As a matter of fact, the point which encounters a lot of pressure on high-heeled shoes is this one here. The heel itself, it has got a very small area of contact, so you must mention something to do with the area of contact. For the high-heeled shoes, the area of contact between the shoe and the ground is very small. That means that the weight of that person, which is actually the force exerted by the object on the ground, is going to exert very high pressure compared to the person who has put on flat-soled shoes, where the area of contact is large, and therefore the weight of that person, remember both people may be of the same weight, but one exerts more pressure than the other one. In this case, for the flat-soled shoes, the pressure exerted by the weight of this person is much, much less, and therefore it will not penetrate the soft ground. Remember, pressure is one of those effects of a force, the penetration effect of a force. Where is the penetration effect of a force largest? It is when the person has put on high-heeled shoes, and less when the person has flat-soled shoes. That's how you would answer that first part. So remember to mention area of contact, and then remember to mention high pressure. When the area of contact is small, there is high pressure. Let's look at the second one, which was about cutting objects or piercing objects. I'm thinking about this thumbnail here. This thumbnail, we use this, or rather tack pins, we use them to fix, pieces of paper onto maybe a notice board or something like that. And you find that just by using your thumb, you're able to drive this pin into the soft board. How is that possible? Again, it's possible because the area of contact between the pin, this area here, is very, very small. So a small amount of force exerted at the thumb head easily drives this pin into the softboard. You may ask me, why is it that then the person doesn't get injured when you're pushing this pin into the softboard? The area of contact between the thumb and the pin is very large. So although the amount of force exerted by the pin on the thumb is equal to the amount of force exerted by the pin on the softboard, different pressures are produced on different ends of the thumb nail because of area. Where the area is very small, that force is going to exert a lot of pressure, and we have already said that pressure is the penetration effect of a force. It's going to develop very high penetration effect, and therefore this section here is going to pierce the softboard. On the other hand, that amount of force will not develop high pressure on the thumb, so the person doesn't get injured. The second one was about when you're using cutting objects such as a knife, maybe to cut this tomato here. You find that it becomes easier when the knife is sharp compared to when the knife is blunt. Again, it's about the area of contact. The area of contact between the knife edge and the tomato is very small. So a small amount of force exerted by the person on the knife, which is equal to the amount of force exerted by the knife edge on the area of contact, that force is going to develop very high pressure on the tomato, and that high pressure may be sufficient to cut that material. So it is easier to work with a sharp knife because you only need to apply a small amount of force. That is why it is easier. You apply a small amount of force to cut. But if it is blunt, to develop sufficient pressure to cut that material or that object, you might need to increase the force significantly. So you see, when you increase the force significantly, you will get tired very easily. And that is what makes it difficult or more cumbersome when you're using a blunt knife. So when you're using a sharp knife, it becomes much easier because the area is very small, and an application of a small amount of force produces very large pressure. Let's move over to the next one. The third one was about this one. Some vehicles, such as transit good vehicles, have many wheels compared to smaller vehicles. Like, for example, I've got this truck here. It's carrying a heavy luggage, which is another truck. You have seen things of the sort. You have also seen these small vans. This small van has just got 4 wheels, but this one has, at the back here, we've got 8. In front here, we've got If you add 4 to 8, you get 12, and then you add 2, you get 16. You see, it has got 16 wheels compared to one with only 4 wheels. Why is this? Why waste all this extra number of wheels while 4 will do? This is what happens. This truck is very heavy. The amount of force it is exerting on the road is very large. So, if the tires were few, the area of contact between the tires and the road surface would be small. That will make the pressure that the tire exerts on the road surface to be very high. And when the pressure exerted by the tire on the road surface is very high, the road surface is going to wear out very fast. So in order to avoid that wearing out of the road surface, regulations are put in place that heavy vehicles must reduce the amount of pressure that they exert on the road surface. And that can only work not by reducing the amount of luggage they are carrying, because there may be nothing we can do about that. If we have to transport this luggage from one point to another, the amount of luggage remains the same. So what else can we be able to do without affecting the force? We look at the second factor, which is area of contact. Area of contact between the tire and the road surface. So if we can be able to increase that area of contact, we are going to significantly reduce the pressure. So you see here in everyday life, there are some situations where we might want to exert high pressure, as in the case of cutting gadgets. And there are some situations where that high pressure is a disadvantage. For example, the wearing out of roads. So back to the point. Over here, the many wheels, they are going to increase the area of contact between the truck or between the tires and the road surface. What that does is to decrease the pressure that the truck exerts on the road surface. So you see, but for the smaller van here, its weight is not so big. So the amount of pressure it exerts on the road surface is just sufficient to provide the necessary frictional force between the tire and the road surface, because that one is also important. Remember, when we looked at friction force, we said that friction force is important. It is the one which pushes the driving tire forward, and if that friction force is not sufficient enough, the tire is just going to skid. So there must be a certain amount of friction force that is necessary. So, and that one comes about when the pressure between the tire and the road surface is sufficiently high, but not so high as to destroy the road surface. So hopefully now you understand why transit good vehicles have many wheels compared to smaller tires. You're going to answer that in terms of the fact that they've got very large weight, meaning that they exert a certain amount of pressure downwards. If the tires were few, the area will be small. That will make the pressure exerted by the tire on the road surface very high, and that can destroy the road surface, making it very expensive for the government. So, in order to reduce the pressure that the tires exert on the road surface, because that is the point you must bring out, in order to reduce the pressure that the tires exert on the road surface, the area of contact between the tires and the road surface must be increased. And that means increasing the number of tires that are in contact with the road surface. Of course, somewhere at the beginning of the video, I mentioned that when these vehicles now they are coming back after offloading, you find that they retract some of the tires upwards. Why that happens is because the the force has reduced, and if the area remains that large, then the amount of pressure the tires exert on the road surface will not be sufficient enough to give these tires the necessary traction, the necessary friction force between the tire and the road surface. So hopefully that helps you in that area. Now let's look at these questions in exercise 4.1. And they are as follows. You are given a force of 100 newtons. You are told that it is applied to an area of 100 millimeters squared. What is the pressure exerted on the area in newtons per meter squared? So let's look at that. So obviously we can say that the force is in newtons. That one is not a problem. But the area is in millimeters squared, so we must convert that into meters squared. So this 100 millimeters squared is the same as, we divide this by 1 million, and that has converted it into meters squared, 1 million. So it's just as simple as that. So this is 1 over 10,000 meters squared, and this is 0.0001 meters squared. What I need you to recall here is that 1 meters squared is the same as 1 million millimeters squared. So you can use that conversion unit. So let's look at the pressure exerted, which is force over area. The force is 100 newtons. Divide by 1 over 10,000. And you find that this one gives us 1 million newtons per meters squared. And it is just as simple as that. Let's look at question number 2. This is similar to one of the examples that I had given earlier on. A girl standing upright exerts a pressure of this much on the floor. Given that the total area of contact between her shoes and the floor is this much, determine the mass of the girl. Now we have already said that when you're given this kind of question, you realize that the force that this girl exerts or this person exerts is equal to the weight, which is mg. Of course, divide by that. So that means that over here, I want to make mass to be the subject so that I can be able to calculate it directly. So when I say pressure is equals to mg over A, it stems from here. And I want to make mass to be the subject, so I can multiply both sides by area. So pressure times area. Pressure times area will give me the force, which is mg. And then I go and divide that mg by the g itself. It will give me the mass. So this one is as simple as this. So the pressure is 13,600. The area of contact is 0.0368, and the value of the gravitational field strength is 10. Of course, that one can cancel out like that, leaving me with 1360. Multiply that by 0.0368. That gives me 50.048. kilograms. You can say it is 50.0 kilograms. Round it to 1 decimal point, and that one will be fine. So let's look at part B. We are asked to calculate the pressure she would exert on the floor if she stood on 1 foot. What does that mean? If she stands on 1 foot, then it means the area has been halved. What do we know about factors which affect pressure? One of them is area. How does it affect pressure? Pressure is inversely proportional to the area. That means if the area is doubled, the pressure is going to be halved. The opposite is the case. If the area is halved, the pressure will be doubled. So here, there are 2 methods you can use. You can just directly quote this and say that the new pressure is going to be doubled. It will be twice. Because the area has been halved, it will be twice this. And that gives me 2 times 13,600. 13,600, yes, that is correct. Go 27,200. So the new pressure is 27,200 newtons per meters squared. That is one way of working it out, because I have reasoned out. If she stands on 1 foot, the area has been halved. That will mean that it doubles the pressure. Or I can go right ahead and divide this area by 2, where now I get the area. Go back and use the equation pressure is equals to force over area. The force is equals to the weight of the girl. I already know the mass of the girl. Multiply it by G to get the weight of the girl, and then divide by the new area. We'll get the same thing. Let's look at question 3. We have already answered this. Trucks that carry heavy loads have many wheels. Explain. Can you be able to remember what we have just said? And remember, when you are looking at how to answer questions, it's always good to identify what to say. Because it's not everything that you say that is going to earn you marks. Sometimes you may have so much to say that the point is lost. And sometimes you may not know exactly what to say. So as you go through various topics, remember, physics is about looking at the way you can use the physical quantities that we study in our everyday life to explain those applications, or to look at the applications of these physics concepts in our everyday life. So when we are talking about pressure and we are talking about pressure in solids, we are talking about factors which affect pressure in solids. So in this example, you must mention something to do with pressure. So the word pressure must appear somewhere in your explanation. The word area of contact must appear. And when you are talking about pressure, you want to say that the aim is to reduce the pressure that the truck exerts on the road surface. Because if the area is left to be very small, then the pressure is going to be so high, and this one is going to destroy the road. So the point is, we want to reduce the pressure that the truck exerts on the road surface. How do we do that? By increasing the area of contact between the tires and the road surface. And that can only be done by increasing the number of tires in contact with the road surface. So let's go to question 4. Question 4 again is similar to one of the questions that I did in one of the examples initially. But there is the idea of pressure. There is the idea of density, rather. The density of the solid now comes in. In the previous one, I had given you the mass of the solid and its dimensions. This time, the mass is not given, but its dimensions, length, width, and height is given. And then we are asked to calculate the maximum pressure and the minimum pressure that it can exert on a horizontal surface. Remember, maximum pressure is exerted when the area is smallest. So between 5 times 3 and 5 times 2 and 3 times 2, which one of these combinations gives you the smallest area? Of course, it is 3 times 2. So for part A, we already know that the area to consider, so this is A, we know that the area to consider is 6 centimeters squared. And this, automatically you convert it into meters squared directly by dividing it by 10,000. Pressure max is equal to the force over area. We know the area, but do we know the force? Right now we don't, because the force is equal to the weight, and weight is mass times gravitational field strength, of course, divided by area. This where something that you have learned before, density is equal to mass over volume, given that, or implying that mass is density times volume, of course, times G, and I have the area there. So this is where now you might want to calculate these or substitute all the values into this equation. The density, this one here, is 8,900. How did I get that? I know something else, that 1 gram per centimeters cubed is equivalent to 1,000 kilograms per meters cubed. We already know this fact. So I've converted 8.9 grams per centimeters cubed into kilograms per meters cubed, because everything must be in SI units. When it comes to the volume, I can see this one will be 3 times 2, which is 6. 6 times 5 is 30. That one will be 30 centimeters cubed. 30 centimeters cubed, I have to divide by 1 million in order to convert it into meters cubed. That takes care of V. G is of course 10. A, I already have it. It was 0.0006. And this will give me the maximum pressure directly. So let me just work it out in one step. Of course, I can be able to reduce certain, like for example, this 0, and this one will cancel with these 2. Then these 2 will cancel with these 2. That makes now the number a little bit easier to manage, because I'm going to have 89 multiplied by 3, and that will give me 267. And then I have 0.0006. That one multiplied by 100, and I have 0.06, 0.06, and this will give me 267 divided by the answer that I've already obtained there, 4,450. 4,450 newtons per meters squared. That will be the maximum pressure that that block exerts on the road surface. Now, if you're looking at this type of question for the first time, it appears as if there is so many things that you need to, it appears complicated. It is not if you've been following my teaching. I've already taught you the concept of density. We have gone ahead and looked at the relationship between mass and weight, and weight is a type of force. We have talked about pressure being force over area, and when we are talking about pressure exerted in solids, one of the forces that the solid exerts vertically downwards on any surface on which it rests is equal to its own weight. And you can see that this question, although it is on pressure, there are so many concepts that you need to remember. You need to remember how to convert from one unit into another. You need to know when to use SI units. You need to remember certain conversion units. You need to remember equations. And you need to know how to put them together. For example, in part B, I'd like you to work out the minimum pressure that it can exert on a horizontal surface. Just use that to practice on that section. Let's look at question number 5. How much force must be applied on a blade of length 4 centimeters and thickness 0.1 millimeters to exert a pressure of 5 million pascals? So again, this one is the application of pressure on cutting objects or on piercing objects. Again, this one is not a difficult question. Why? You see the length and the thickness of the cutting blade is given. Go the length there and the thickness. When we look at the cutting edge of a knife, this may be what we see. The length, we've been told that it's 4 centimeters. The thickness here is 0.1 millimeters. We want this area of contact between the blade and whatever is being cut. So that area, let's use similar units. I'm going to use centimeters, or let me use millimeters. So this one will be 40 millimeters times 0.1 millimeters, and you find that this gives me 4 millimeters squared, which will be 4 divided by 1 million meters squared, because I must express the area in meters squared. So when it comes to working out the pressure, remember that triangle that I just taught you previously, that when you divide force by area, you get pressure. So if we are looking for force, we cover force with our hand, and therefore force becomes pressure times area. That pressure is 5 million newtons per meters squared times area in meters squared, 4 over, again, 1 million. You see how the millions cancel out, and I end up just getting a force of 20 newtons. So you can see when the blade has got a very small area, I just need to apply a small amount of force and it develops very large pressure. So the penetration effect of the cutting edge into what you are cutting becomes very, very high. And this is how you would answer those questions. In our next section, we are going to look at pressure in liquid.